So you are from the University of Bristol and you are here at EuRoC. So what are you doing here?
So we both work at the University of Bristol. We're staff, we're faculty. So my name's Dr. Steve Bullock. I work in our flight lab. Most of my work is with drones, and a lot of our colleagues in the flight lab work with drones for good. So search and rescue, disaster relief, conservation, scientific observation. We fly drones over volcanoes and giraffes and all sorts of things. I feel very lucky. And then my theoretical work is in control and path planning for multiple drones together. And I'm here because my students brought me in maybe 2 years ago to work on a payload for one of their rockets, which was going to be a drone that came out and flew back to the launch pad. They haven't quite got there with the payload yet, but they're making really good progress with the rockets.
Hello, I'm Dr. Laura Rianne Pickard, and I am a composites researcher in Bristol Composites Institute, which is part of the University of Bristol. So I'm here because composites are great lightweight structures for making rockets, and I was approached by the team about helping them, getting them into our composites lab so that they could carry out manufacturing. And along the way, we talked about some new and exciting things we might be able to do. And this year we have a new coupling, which the Payload sits on, which is inspired by the skeleton of a sea sponge. So it's a bio-inspired structure. And it's designed to perform extremely well under compression, because it's compression loaded in the thrust. And it's achieved double the ultimate specific failure strength compared to a standard baseline shell structure. So students have done a fantastic job. That was all carried out by the design, build and test team from our Centre for Doctoral Training and Composites. It's great to see it integrated with the rocket, and I look forward to getting flight data from it when it launches.
So this coupling is basically a lattice made out of composites?
Yes, that's right. It's a lattice structure. The longitudinal members are pultruded carbon fibre epoxy rods, and they're reinforced with an overbraid. So same principle as braiding your hair. You have strands going in and out of each other, and they go around the rod, grip it very tightly, and there are little broken fibres which extend out away from the braid, and they give you very good contact between the fibres and the surrounding epoxy matrix, which improves the performance of those rods, and they're combined with hoop and diagonal members.
And this would achieve twice the specific strength of a solid composite coupler?
Yeah, so it was tested just under compression. We had 3 of the baseline cones, which are just thin shell cones, and 3 of these lattice cones. And yet, per unit mass, the ultimate failure strength was approximately double for the lattice cone.
And you also work at CERN, and what is your role there?
So I have a collaboration with CERN. They approached me a while ago now about solving a problem for cooling the particle detectors that sit in the Large Hadron Collider. So the electronics sit on composite panels, and those electronics get very hot, so they need to be actively cooled. And what they do is, at the moment, they pump coolant through pipes, which are made of titanium or polyamide. But there's a mismatch in coefficient of thermal expansion between those pipes and the surrounding composite. They also have a little too much high mass material for a detector, so they want to move away from that. So they were working on making composite panels with embedded channels within the composite itself through which they could pump coolant. They can make those really well, but they can't reach the required burst pressure without extra reinforcement, and that's where my work comes in. So I worked with them to reinforce those channels using exactly the same fuzzy overbraids that we use on that rocket coupling, so just same principle in a different application, and that gave us approximately an order of magnitude improvement in burst pressure.
So you basically reinforced the channels inside with this kind of matrix reinforcement on the outside.
Yeah, so it's a braid. So you make the channels by including a filament of polylactic acid, same sort of thing you put in a 3D printer. And when you've made your composite, you vaporize that filament off so it leaves a channel behind. So what we did was we braided over the filament before we included it in the panel, and that braid made a huge difference to the burst pressure.
Okay. And your work in, you said that you also work in volcanology with your drones, and so what do you study there?
So our flight lab has a range of different collaborations, and we do a lot of really fun applied work. So the volcanology collaboration is with our colleagues in Earth Sciences at the University of Bristol. So we work with them to gather scientific data, which is everything from 3D models of the volcanoes through to sampling the gases that are coming out of the volcano all the time, through to catching ash as it comes out of the volcano. So we have some really cool work. I'll reference my colleagues, Professor Matt Watson and Professor Tom Richardson. And if you look up their names, you'll see some papers about aircraft autonomously flying through volcanic plumes and things like that. And then other work includes things like Wild Drone. If you look up wilddrone.eu, it's led by South Denmark University, but there are, I think, 12 different institutions over 9 different countries around Europe and the UK and Switzerland as well involved. So there's some really exciting stuff there with conservation, and then I have some other work about plant conservation as well. So it's just really cool what you can do, like extending capabilities with drones. We can, aerial data is really important, but also kind of using the right tools for the right jobs. So the really interesting thing we have going on at the moment is we have a CubeSat under development. It's a project called Prove, which is about taking observations of volcanic plumes from space. Our students are building a CubeSat. We have a satellite laboratory at Bristol. And the long-term aim for that is to fuse the data from satellites with the data from drones, with the data from ground-based observations, so you can get a really detailed model of the volcano plume in 3 dimensions, which is more challenging from a single point of view. And yeah, I mean, we have so many different ways of gathering data these days that I think the next step to make things more useful is to start using all that data together. But it brings a big problem with the data management, the data science side of things. So yeah, the flight lab is a hub for lots and lots of different technologies. And in some ways, we're looking for interesting uses to do good with the technology that we have. I like getting my students to think about the ethics of what they do. And obviously in Rocketry, there's a wide range of things as well. So it's been really fun working with the students on this project as well.
Okay. Okay, and I saw that the Hypower Bristol team made a lot of progress from last year in their rocket. So how do you think they managed that?
We're so proud of our students. They've come a long way since I started being involved with them a couple of years ago, and they had a solid rocket last year, and they've moved to a liquid engine in a very short space of time. And they've had some really big challenges, both with the technology development and with the testing. And they were only testing last week with their hot fire tests, which it would have been nice to have more opportunity. But the biggest challenges were the logistic ones. I think they were partnered with a test site, and they had to change plans at short notice. And the thing that's impressed me the most has been the flies are getting to me. Just their persistence, and they've managed to find new industrial partners at short notice without annoying anyone too much as well. I think it's difficult when you're a student team. So their success, I mean, they're not launching. They had a tank failure during one of their hot fire tests last week, which I know they're really, really upset about. But I consider them sort of 99% of the way there. The hardest thing is getting to the launch pad, right? So the things that the strengths that they've shown are their working together on the scientific side of things and the engineering design side, but also their persistence in funding, in collaborating with industry, and working with the faculty as well. I was quite surprised that there are not as many academic staff here as I had expected. Because it's such a good opportunity for collaboration between the students and the research that universities do. So Laura Rianne's work with Composites is a really good example of what I want to do more of. I think pretty much every single part of the rocket could be an undergraduate or a postgraduate research project. So I'm going to state this now. You can see next year whether we achieve it. But I really want to get as many student research projects as possible involved with and on to next year's entry. Yeah, more of what you're doing. So the fact that we have such a good staff-student relationship in our faculty, the fact we have some amazing facilities that we use for research, but the students also have access to for their project work, I think is a real advantage for our team. I don't know how you feel about the collaboration that you've had.
I think it's been fantastic. One of the real strengths of the Hypower team is that they brought together people from different disciplines across the university, across the faculty. We each have our little individual research teams, and it's so easy to just get stuck in your little bubble. So a project like Hypower brings us together across that, encourages lots of collaboration, and it's been great to do. I've got to particularly shout out team leader Lillian Macbeth, without whom this would not have happened. She is a fantastic leader, and you can really see how much the team respect her and how well they work together.
I think that the whole team has been amazing, but there's definitely a core that have been in it from the start and really pulled things together. So I'm looking forward to seeing how the newer students develop into those roles as well as the more senior students graduate. I really like seeing the student development that we get from this. And we've got a really cross-disciplinary team as well. Lily is a civil engineer, which everyone says, oh, why is a civil engineer getting involved in rocketry? Lily aspires to look into the infrastructure side of rocketry. So she's making PhD applications this year for launch infrastructure, environmental considerations and things like that, which is really exciting. We have engineers from across the faculty, but we also have people from outside the faculty. The team has worked with geographers on payload missions and things like that, and it's just really cool. It's rocketry is cool because it is, but the things that really inspire me are the opportunities for kind of making connections, for developing students, and for developing the links and opportunities that the staff and students have. I could talk more about that. I can talk about that all day. That's why I do my job, I think.